Okay, so now that we know our estimation for the order of magnitude of the molar fluxes of ethanol or methanol, I believe, I'm getting their names mixed up, methanol and acetone to be 10 to the negative third from part 1, we can now use Python and Google Collaboratory to help us solve example 1-17. So we're going to start with the most basic way, and that is to import our tools that we need to solve this problem. So we're going to import NumPy as NP, which is a standard importation and abbreviation of numerical Python, which is a big catalog of mathematical tools that help you solve problems like this. So we're going to import NumPy as NP, and then we are also, if we think about this problem, we have differential equations, right? And we have initial values for those differential equations. So we're going to be solving an initial value differential equation problem. So we're going to import, and then from the SciPy catalog, another big catalog, we're going to, and if you think about it, initial value problem equations are actually integrations. So you're integrating. So we need from the integrate into, if I can spell correctly, integrate catalog, we need to import the solve IVP function, and that'll allow us to solve initial value problems. So if we think about this problem, we have initial values, correct, but we also have unknowns in the molar fluxes of these components. So what we're trying to find out is that when these mole fractions are 0, what are those corresponding molar fluxes? So that would be a root solving problem. So when you're solving roots, you're optimizing. So we need to go back into the SciPy catalog into optimize, and we need to import SciPy optimize as and then a root, because we'll be solving for roots. Next, we would like to graph those, right? So when we graph these, eventually we're going to want to graph the data points as corresponding to eta on the x and mole fractions on the y, excuse me. So we want to import things that are going to help us graph. So we're going to import Plotly, which is just a Y tool for graphing, and then subplots, import Plotly, subplots as, and then make subplots. And then we are going to, these are all wrong, excuse me, these are all wrong. This should be from, except for that. We want to do from these catalogs we're importing. Yeah, that's my mistake. Fix this right now. So from these catalogs, we are importing these functions. So we're importing the root, importing the solve IVP, and importing optimize. So yep, so from these, not import. I got mixed up. So from Plotly subplots, we're importing make subplots, and then we want to import, and then we want to import Plotly dot graph objects, and then we want to import that as geo. So graph objects are things like scatter plots, which eventually we'll use. That's what we want to use. We want to use scatter plots to graph these data points. So we want to import the Plotly graph objects, scatter points as geo, which is shorthand to make it easier. And then we also want to import, now this is totally optional, but I think it looks better. So plotly.io as PO. And then that allows us to change PO, the template of the graph, to whatever we want. So we're going to set the default equal to, and then we're going to say plotly underscore dark. So that changes the background of the graph to dark. I'm sure some of you have done this as well, is change your phones to dark mode. So you can see this, even this Python is now in dark mode. So now that we're done with that, good, no typos. That was actually incredible. I don't know how I would have done that. But all right, moving on to some of the given parameters of this problem is that we're given the Stefan-Maxwell pair of diffusivities. So we're given these in terms of millimeters squared per second in the book, and we transform them to meters squared per second. And we're given the pressures and temperatures, and the pressures in Pascal, temperature in Kelvin, and then we know the gas constant in terms of joules per mole Kelvin is 8.314, and that allows us to calculate the concentrations of the vapor phase of this gas, assuming it's ideal, and that concentration is equal to the pressure over the gas constant times the temperature. And then we also know that delta, or the tube length, is 0.24 meters. Now, when we were scaling in part 1, our goal was to get the independent and dependent variables on the scale from 0 to 1, and we did that by making eta z over delta. In doing so, we made the right hand of the equation include a delta piece in the denominator. So we are combining the denominator here in terms of the Stefan-Maxwell relation equations. The denominators of those was normally just the concentration times the Stefan-Maxwell diffusion coefficients. However, with the scaling that we did, there was also an extra delta that was put on the bottom. Well, it was on the top, however, you can put it divided by over the bottom, and that's why it's divided by delta. So we are essentially grouping these denominators together, and it makes it easier in the calculations to come. N1i and N2i are our initial guesses, and that is from the order of magnitude estimate that we did in part 1. That allowed us to check the orders of magnitudes of the variables already in the equation that we knew, and then from that we deducted that the molar fluxes had to have an order of magnitude of 1 e to the negative third. And then we're also given the mole fractions of the methanol and acetone at the liquid interface. So moving on, we're going to start with the initial value problem that we set out to solve. So when we look at initial value problems, we need fun, not the kind of fun I'm having in this class right now, but the fun is function, so we need a function, and if we scroll down we can see the parameters for function, so it needs to be callable, and the function is the right hand side of the system, and the calling signature of it is the independent variable comes first, followed by a vector of the dependent variable. So in this case, the independent variable would be eta. It was scaled and from 0 to 1, and then the dependent variable would be the mole fractions. So we need to make a callable function in order for us to solve an IVP. So let's go ahead and try and do that. So let's go ahead and define a function, and let's call it dy. And like I said, you have to immediately start with the independent variable, and that, like I said, is eta, followed by the dependent variable, which is y, so the mole fractions. So now we're going down. So now we have to make an array of those dependent variables. And when an array is made in Python, they thought it would be fun to start the indexing at 0 for some reason, because I don't know why. Anyway, so we don't want to get caught up in that and calling y1 y bracket 0 the entire time, so we're just going to, as Carlos says, waste some CPU cycles, and we're going to say that y1 is equal to y bracket 0, which is the first element of that array, and we'll do similarly for y2. Say it's equal to y1. Okay, and then mole fractions add up to 1, so we can say y3 is equal to 1 minus y2 minus y1. It's getting dark out. I think I might need to turn on my backlit keys. So now moving on, we need to return that right side of that system of differential equations. So we need to return an array, return NP for numerical Python, array, and then we need to parenthesis, bracket, parenthesis, because we're starting on the top of these. So now we're listing out the right side of those Stefan-Maxwell relation equations, and we're going to start out with the right side of the first one, which is y1 times n2 minus y2 times n1, get out of the parentheses, F12 or F12. Again, that's grouping together the concentration, the Stefan-Maxwell diffusion coefficient, and delta into one nice handleable or usable part. All right, and then minus y3 times n1, and that one is over F13. So now we can comma, move on to the second element in this array, which is, we got to start new brackets or new parentheses again, and this is the second right-hand side of the Stefan-Maxwell equation, and that is y2 times n1. I could be saying, it's a mouthful to keep saying the molar fraction of 2 times the molecular or the molar flux of 1, but you get it, I think. And then minus y1, mole fraction of 1, times n2, and get out of the brackets, over F12 again. Remember the reversible. F12 is F21, just the same as D12 is the same as D21. And then minus, and then y3 again, times n2 this time, and those are over F23. Okay, so now that we have the array of the right-hand side equations, we are going to attempt to solve this initial value problem. So let's start by putting in the function, right? The callable function we named dy, followed by the time span. In this case, is what you want to integrate over, and that is eta, which goes from 0 to 1. And then we want to, what's next? The initial guesses, which would be y1i and y2i, followed by the method, which Carlos says do this one, and I believe him. So Rodau, I always spell it wrong. Yep. Okay, there we go. And then followed by the dense output. We want to dense output equal to true. That way it allows us to input any value of eta and get the corresponding values of the corresponding mole fraction values of methanol and methanol and acetone at those etas. Okay, so now that we have that, shift enter, and hopefully we don't get an error. So it did, the solver successfully reached the integration interval. That's good. And here at the solution, we can tell it's a dense output, and that we can get the answers by saying, by using, now we can say like let's go res IVP. So the result of the initial value problem is equal to that. So we can say res IVP dot solution, and then plug in 1, which would be at the very top of the tube. Shift enter. We should get, so we should get 0 and 0, because, right, if we think about this, at the top of the tube, the air is flowing so fast, it's in such a high concentration, the mole fraction of air is 1. If the mole fraction of air is 1, the mole fractions of the other components have to be 0, because mole fractions add up to 1. However, we are not getting that. We are getting a negative number and a number that's not close to 0. Well, if we think about that, that makes sense, because our calculations are based on guesses. So the guesses for N1 and N2 it just doesn't make sense. It's a guess. So why would we get the right answer? That would never happen. So now we have to figure out the mole fractions are equal to 0, right? That's where we want to find out. So the mole fractions are equal to 0, and I plugged in 1 for a reason, because at 1, like I said, the mole fraction should be equal to 0. So when we want to solve for 0, we want to use a root finder. So if we use the root function to try and find where the mole fractions are equal to 0, it should give us the corresponding molar fluxes for those mole fractions. So if we look at root, go ahead and look at root. So if we look at root is similar. It needs a function, a callable function, and it needs initial guesses as well. So let's define another function, because we're going to have to define another callable function that we want to, whose roots we want to find. In this case, we want to find the roots of n. So we want to adjust the molar fluxes in order to get the 0 mole fractions. So we need to nest this mole fraction, IVP, inside of the molar flux root solver. So again, we're making an array, or we're calling out a function, and we want to make sure that n1 is equal to n, again, 0, because the indexing is super fun. And then n2 similarly is, in this case, the second element, or n1 of the array. So this all needs tabbed. All right, so now that we've done that, we need to also, so basically we put a root, or a IVP initial value problem, within a root solver. So now we want to return, and then we want to return that value. So we're going to turn, let's set, res IVP solution. Now let's see what we get. So now that we've done that, let's see. Okay, so we returned the that for that. So I just said that for that. We returned the solve IVP as solution at 1, right? Now let's try the root function. So the root needs a function, right? We made that callable function f. So, and then it also needs the initial guesses, just like an IVP. So let's give it the initial guesses. I believe they should be in brackets. N1i, or the initial guess we had, and N2i, the initial guesses for molar fluxes. And let's go ahead and shift enter. So it says the solution has converged, which is good, and this answer is stored in the x value. And looking at it now, I've done this several times, so I know these answers are correct. But how would you know these answers are reasonable without knowing that you've done it 16 times? And the fact that your answers should be, what, if we look back up here, our guesses are 10 to the negative third. The magnitude should still be the same. The values won't, but the magnitude should be 10 to the negative third. So if we look within these magnitudes, you can see that they are 10 to the negative third, which makes sense. And also having a book that has similar answers with a little bit error due to rounding also tells you that you're heading in the right direction. So now that we have the correct molar fluxes that correspond to the 0, so we found the molar fluxes that at those molar fluxes, the mole fractions at 1 should be 0. So now we want to redefine this function right here, because it's within a function, so it's not going to allow us to graph that if we don't redefine it again, or basically use it again. So basically we're going to brute force this, as Carlos says, and we're just going to copy and paste this down to here, and then we're going to add a little bit. We're going to have to redefine N1. So now that we know the molar fluxes, we can say the res, let's set this equal to, let's set this equal to res root. I like that better. Res root is equal to that. So N1 is equal to res root, and then you can call a function out of this array, because we know that array is these values right here. So we can say res.root is that array x, and then the first element in that array. And then N2 similarly is equal to res.root, and then res root. Our brain's in a blender. 1. Yeah, that looked good. Okay, so now that we have given N1 and N2 their proper correct values, I think, yeah, if you look at them now, you can see that they're given those values from their array, which is good. You can kind of hover over them and it'll kind of tell you what values they have. We can go back to graphing, which is what we really want to do, is we want to graph these solutions. So go ahead and run this unexpected indent. Okay, I think I would. Give me a second here. Okay, this should be over here. Let's try this. I think this is right. Give me a second. I'm trying to think. Let's try this. Okay, there we go. Okay, I just had a wrong indent. Unfortunately, that is a love-hate relationship with coding. Anyway, so now we want to graph these results that we have. So we want to create data points to calculate those values. So let's make a plot, and then we're going to use a function or an ability using numerical Python that's called linspace that creates points equally spaced, return evenly spaced numbers over a specified interval, which is good. So we need a start, stop, and then how many numbers. Okay, so I like starting from 0, going to 1, and then 51 numbers gives you evenly spaced digits in this case. So we're going to go ahead and enter. So a plot would essentially, we're creating our x-axis right now. So now we need the y-axis or the mole fractions, and the mole fractions are the values that we get from that. I poked my screen. I should be pointing with the cursor. We should get from the res IVP. So what we need to do now is we need to say, let's call this solution. So our y-axis solution is equal to res IVP dot solution, and then we want to run the equally spaced data points through the calculation. So we want eta plot there. So those numbers would then go through that res IVP solution. So now we want to make the actual graph. So now we want to say figure is equal to, and then we'll say make subplots, and then let's look at what make subplots need. So we want to make one graph. We want to overlay the three curves on one graph. So we need rows, is what it says, rows equal to 1, comma, columns equal to 1. And then we want to give these titles too. I like giving them titles. So the x-axis will be called eta, and then comma, and then the y title will be equal to mole fractions. That's good to me. Okay. So now that we have named our graph, what we want to do next is add the lines that'll connect the dots that we have, the data points. So we want to say the figure, and then we want to add a trace line, and then we want to add a graph object. In this case, we want to make it a scatter plot. So again, GO, because we shorthanded it up front, we're making a scatter plot. And that scatter plot is, we need an x-axis. We need to physically describe the x-axis. So the x-axis will be, thought I was far enough, eta plot will be the x-axis values, and then we want to say the y values are, they'll be the solve. So the solve. So we want to say y is equal to, and then we want the first, we're doing for acetone right now. So the first one will be y0, or the first element of the y's will be, and then we want to say name, I believe, name equal to, yeah, that looks right, name equal to, and then that is acetone. So let's say shift enter and see what it is. Okay, that looks good to me. So let's go ahead and control C. Do that a couple more times. So the second element would then be methanol. And the third element is air. However, it's not Y3, it's mole fractions, right? Remember that the y-axis is mole fractions, so we're doing 1 minus. Seems fairly logical, but makes sense once you see it, but it's an aha moment for sure. You just do 1 minus the other things, and you'll have the mole fraction of air, because like I said, the sums of mole fractions of air add up to 1, so we only need to find, or only need to put acetone and methanol through the sol function. So shift enter should put the other 2 lines on there. That's weird. I think I messed up here. Hold on 1 second. Air. Wait, is this right? No, it's not, because this air should be going to 1. Give me a second. Let me figure this out. I can figure this out. I'm going to snap my fingers and do movie magic. Boom, it's done.